Hello, in this video I'm going to talk about parametric equations. So this is a little introduction to the parametric equations, and then I'll have another video that goes a little bit deeper into them and the calculus involved in parametric equations. But first we need to start with what a parametric equation is, because I'm guessing that a fair number of you have not had this in your mathematical history. We don't talk about it in pre-cal, and I'm pretty sure there's not a class in high school they talk about it unless it's in some of the AP calculus classes. So basically, a parametric equation is equations. Parametric equations are equations that have a third variable, otherwise known as a parameter, that determines the x and the y. So normally in a normal equation, we have something like f of x equals 3x plus 2 or something like that, which we can also write that as y equals 3x plus 2. And so we say that y depends on x, meaning that I can plug something for x and that will determine what y is. So in a parametric equation, there's actually, I should say parametric equations, there's actually two functions that are both x and y are a function of a third variable. So for example, we could have something like x of t is equal to 2t and y of t is equal to t squared. So these would be the parametric equations. And t would be called the parameter, the third variable that the other two depend on. So this is basically, we have an equation for finding the x and y coordinates. So for example, if I let t equal 1, then that's going to produce x of 1, which would be 2, and y of 1, which would be 1. So that would produce the point, the ordered pair 2, 1. And you could actually go and graph that point. And so that's what's kind of unique about parametric equations is there's three variables. Two of them show up on the graph, but the third one never shows up on the graph. Well, it kind of does, but we'll get to that in a minute. So just like I would graph it, I'm really just graphing a normal xy plane here. So this would be over 2 up 1. So that would represent the point, and this point happens when t equals 1. So then we could also say, well, let's let t equal 0 and see what happens. So that would give me x of 0, which would be 0, and y of 0, which would also be 0. Again, I'm just plugging it into these formulas up here, these equations up here. And of course, that would be that point right there. So that point happens when t is equal to 0. And let's do one more just for fun. Let's let t equal 2. That'd be x of 2 equals, if you remember the equation is 2t, so that would be 4. And y of 2 is equal to, that'd be t squared, right? Which would also be 4. So that'd be point 1, 2, 3, 4 up 1, 2, 3, 4. And so then that point occurs when t equals 4. And of course I could keep plugging in points for t, and I keep getting points out for, get out numbers for both x and y, which would produce a coordinate pair, which would produce a point on the graph. And you could see that I could draw a continuous graph from this. In fact, it looks like maybe it might look kind of like a parabola. Let's check actually and just see what about if t equals negative 2, what do we get? Then x of negative 2 would be negative 4, and y of negative 2 would be positive 4. So 1, 2, 3, 4, up 1, 2, 3, 4. And yeah, it looks like that might be the case. It might be a parabola. So the point is that you have this third variable known as the parameter that's determining the x and y values. So we would say that x is a function of t and y is a function of t. Now the cool thing about this is normally when we draw a graph on the xy plane, when it just involves x and y, which by the way is called a Cartesian equation. We're talking about parametric equations. The normal ones you've been dealing with are Cartesian equations. But normally when we graph a Cartesian equation, there's no real direction. So if I was just to draw a graph like this, if someone said, well, which direction are we going? That would be nonsense, right? Because there's no real direction to this. I mean, they don't have any order as far as when do I do one or the other, right? I can go. The difference between that and parametric equations is there is a direction. So usually when we'd call this a curve, when we draw the curve that's related to a parametric equation, sometimes we call it a path because there actually is direction to it. Because basically what we say is that as t gets larger, that is the direction that you're moving. So you can see that if we were to connect these dots, I don't know exactly how they go, but they probably go something like this. So that means that this path would have a direction like that. It's going from left to right and from low to high. So these arrows, so there actually it would be arrows on this graph. And usually we have, in a parametric equation, we have a initial point and a terminal point. Because often when we do parametric equations, just a minute, we have a domain on t. So you might say that t is between 0 and 4, let's say. So then if we were to graph this, we'd go back up and we'd forget about that one now. And that would be the total graph because I'm only graphing when t goes from 0 to 4. And we would say that the initial point would be here at 0, 0, and the terminal point would be up here at 4, 4, because the path begins at 0, 0 and ends at 4, 4, based on this right here. Well, actually, I'd have to have equal to here, there. And as long as we're talking about it, we could do this in a different notation by going like that, right? Which is normally all I would use is interval notation. Okay. So that's the idea of parametric equations. So as we just said, you should be able to, given a t, be able to find the x and y that go with it. Also, for that matter, if I let x, let's say that we know that x is equal to 2, then you should be able to find out the y that goes with that. Of course, we know what it is, right? Because we already did that up here. It's 1. But let's say we didn't know that. We would just say that we know that 2t is equal to 2, which means t is equal to 1. So if I want to know the y that goes with it, the y that goes with that x, that would be y of 1, which of course would be 1 squared, which would be 1. So the y that goes with 2 in this case would be y equals 1. So that would give me an ordered pair. Okay, and likewise, let's just, because we already did that one, let's do a different one. Let's say that we knew that x is equal to 6. Well, then we do the same thing. 2t is equal to 6, which means t is equal to 3. So that means that y of 3 would be equal to 9. So that means the point 6, 9 would go on that same point, on that same graph. That would be 9 would be the y coordinate that goes with 6. Okay, which actually confirms to us that it's not a parabola, doesn't it? Oh yeah, well actually it still could be a parabola, just as has some kind of a stretch on it. Yeah, it looks like it might be a y equals 1/2 or 1/4 x squared. Yeah, I bet you that's right. 1/4 of 9 1/4 of 36 would be 9, yeah. So now, actually, for that matter, let's go ahead and find that out. So the other thing you should be able to do with parametric equations is you should be able to, if it's possible, convert the parametric equations into one Cartesian equation. So again, if we have x equals 2t and y equals t squared, then we can easily ascertain that t is equal to x over 2, right? Which means y would have to be equal to x over 2 squared. And that would give me y equals, sure enough, just like I said, 1/4 x squared. And so it is a parabola, just like we suspected. It's a parabola with a stretch factor of 1/4, a vertical stretch factor of 1/4. And that makes sense when we look at that picture because it looks like a parabola, doesn't it? So that's converting parametric equations to a Cartesian equation. Here's my parametric, and there's my Cartesian. Now, when you're converting from parametric to Cartesian, you have to be careful because sometimes the one of the two parametric equations might have a restricted domain on them, which means you have to take that into consideration when you go to write this equation. Now, in this case, we didn't because x is all real numbers are possible. Same thing with y. Oh, actually, no, y isn't, but that's okay because we still have, because, well, let's see. Y is cannot produce any, yeah, can't produce any negative numbers, and it still can't. So, so you have to be careful of that. And in the next video, I'll do some examples where the domain in the parametric equations affects the Cartesian equation. I'll show you how to do that. Okay, so that's an introduction to parametric equations. We didn't get into the calculus side of it yet. So in the next video, I will talk about some more complicated examples of converting from parametric to Cartesian. And I'll also talk about the calculus behind it, because we want to be able to take the derivative and possibly integrate these. So that'll be coming up next. You can get excited about that.